I'd like to welcome everyone here. I was here last year and it's a beautiful city to be in. What I'd like to do today is try and give some insights about the uses of probiotics and prebiotics in animal and human medicine and how we can take a more targeted approach. And I think people working in veterinary medicine are really at the cutting edge here, and that they're able to contribute to this area of presentation. What I'd like to focus on initially is talk about the commensal microflora, the microbiota in the intestine. And I'll then talk about how we can manipulate the microbiota for therapeutic purposes. And then I'll talk a bit more specifically about these probiotics and prebiotics. And again, I'd like to focus on symbiotics, which I see as perhaps the way of the future for probiotic research in this arena. And I'll just finish up by talking about some of these topics here. In terms of the commensal microflora, in actual fact, the microflora contains a lot of bacteria known as the microbiome, as well as some fungal elements as well. So there's about 200 to 400 of these are actually cultivable. So what that basically means is the vast majority, 15 to 36,000 of individual species, you can't actually cultivate at all. So again, many of these have to be detected by other techniques. So there's a huge diversity in the microbiome, and this is the huge number of organisms that we have. And in reality, there's 100 times more microbial genes than human genes. So what this is saying is that there's basically more of them than there are of us. So we are really the parasite, if you like, in this situation. Most of those bacteria in the microbiome are anaerobic, and they fall really into these four divisions: the firmicutes, Bacteroidetes, Proteobacteria, and Actinobacteria, and they're the relative abundances. And there's a regional variation in the composition of those bacterial species, and they increase in concentration as you move distally down the intestine. Now, it's very interesting. I work in a children's hospital in inflammatory bowel disease research, and we're focusing on the breakdown of these different organisms. And people, or certainly children with inflammatory bowel disease, have got far less diversity of those four divisions than healthy individuals. So that's something we might want to come back to a little bit later on. Again, this is just reiterating what I just said, the very relatively low numbers in the stomach. As we move through the duodenum, the numbers start to increase. The distal ileum, this is in hindgut fermenters, of course, 10 to 7 to 10 to the 8th. And as we move down to the colon, it's very sizable numbers of organisms. And I'd like to talk a little bit about the way we can manipulate those today. Of course, in those organisms, that massive spectrum, we have a lot of bad guys, the enteric pathogens, and I've just listed some of them here. And of course, in a normal situation, we have these present in very small amounts, and they're completely overwhelmed and swamped by the so-called healthy commensal bacteria. And most of you would be familiar with these conditions from some of the animal studies that you've been working with in the veterinary arena. In terms of the interaction, it really is very complex between the bacteria and the microbiome in the intestine and the interface with the human lining of the epithelium. There are these toll-like receptors and nod-like receptors, which are basically involved in bacterial sensing. And this NOD2 mutation was found about 10 or 15 years ago now in inflammatory bowel disease, and was the first mutation that was associated with a defect in bacterial sensing in many inflammatory bowel disease patients. Conversely, on the other side, from the host, we have the bacteria themselves, and they have receptors and molecules on their surface which are involved in this sensing process. And these are just two examples of lipopolysaccharide and flagellum being on the surface of those bacteria. But of course, bacteria also release factors such as proteins and bacteriocins, which can be involved in killing other organisms, but can also be very helpful. And I'll come back to that a little bit later when I'm closing my presentation about what I see as the way of the future, because it involves probiotic bacteria releasing factors which can be beneficial. As I mentioned before, inflammatory bowel disease is perhaps the archetypical condition in humans where there's a defect in the barrier function of the intestine, where we have a an imbalance or a dysbiosis, as we call it, between the commensal bacteria and the pathogenic bacteria. And this is a condition that's really very prevalent, and it's one that I work in quite frequently. But in the veterinary arena you'd be more familiar with it, Johne's disease, which is basically the animal equivalent or the livestock equivalent of Crohn's disease in humans. And in Johne's disease, this organism here has been implicated, and of course it's always been pursued as a potential agent in the induction of inflammatory bowel disease in humans, but that's never been proven. It's really been associative. But what I do remember very clearly, because this organism was actually discovered by an Australian pathologist, and who subsequently went on to get the Nobel Prize, Barry Marshall, found out that this organism was causative of gastric ulcers. And we all remember that gastric ulcers, once upon a time, were caused by stress and acid production, and in actual fact it was caused by this organism. So at the back of everyone's mind in inflammatory bowel disease in humans is that there could be a single causative pathogen, and that's yet to be discounted. So I mentioned before about the dysbiosis inflammatory bowel disease. In inflammatory bowel disease, or IBD, there is a decrease in microbial diversity. They don't have as much spectrum of bacteria than healthy individuals, and the same is true in Johne's. And it's characterized by these increased numbers of these organisms and decreased numbers of firmicutes. And it's also interesting that this dysbiosis is now being associated with a range of different conditions, such as chemotherapy-induced mucositis, which is what I work on when I'm wearing my Cancer Council hat, and also in a different scenario with obesity. So this manipulation could be very important for something like obesity in humans, pig production in animals, and general health. So I think this is a really growing area in terms of manipulating the microbiome. So as I mentioned before, in this very simple situation, in something like inflammatory bowel disease, we have an imbalance of the pathogens here. This is clearly a colonoscopic view of a colon with inflammatory bowel disease. This is a healthy colon. These are the normal microflora, and this is the imbalance with the pathogens. So having established that, how can we basically alter that balance back to normal? And probiotics is an area that's been basically pursued since the First World War. In fact, the first probiotic was developed in 1917 in the First World War, although they didn't really know why it was working. But most probiotic bacteria tend to be lactobacilli and bifidobacteria. And by definition, and again you can read this out yourselves, they're living non-pathogenic microorganisms. Very fluffy definition of exert a positive influence on host health. So basically it's something which is beneficial, but what is missing there is insufficient numbers, because there has to be a certain dose of probiotics to have a healthy effect. And again, probiotics anecdotally and also more recently scientifically have been indicated for a number of conditions characterized by inflammation, such as arthritis through to radiation enteritis, which is one of the conditions that I work on myself. So again, the mechanisms are really very complex with probiotics. And the question is, do they have a role in bowel disorders? And there are a number of questions. Which probiotics should I use? How much do I need to use? How often do I need to administer that probiotic? And how do I assess whether the probiotic is efficacious? And we've managed to work our way through this little roadmap and hopefully come up with a strategy to develop probiotics and prebiotics in a far more targeted way than is currently being used at the present. In terms of the mechanism of action of probiotics, most of them will work by simple adherence to the epithelium and simply competing out the enteric pathogens. It's a simple play a game of numbers, basically. They can also modulate the mucosal immune system, modulate the apoptosis and proliferation ratio, basically altering cell birth and cell death, and also, as I mentioned before, producing bacteriocins and other factors. And there's also some mechanisms which are starting to be indicated now, which have yet to be proven. So basically, it's really a complex situation here, but it depends on the nature of the probiotic. And I think this is a real take-home message, that probiotics have to be indicated for individual animal species, individual bowel disease conditions. We can't just go down the health food store, grab some probiotics, try it in a certain situation and expect it to work. That wouldn't work if it was antibiotics, so why should it work with probiotics? As I mentioned before, the first probiotic was described back in 1917, and it was an E. coli by a chap named Alfred Nissel, who was a surgeon in the First World War, and he happened to notice that a lot of his soldiers had very severe diarrhea, but some of the soldiers didn't have diarrhea. So he cultivated the feces of both groups of soldiers and found out that the ones that didn't have diarrhea had this E. coli organism. And it's since been called E. coli Nissel 1917, and it's marketed very widely, and there's a lot of scientific studies being done on that in terms of measuring its effects on the immune system and on barrier function. And it's actually being used medically now and being found to be as effective as standard conventional therapy for ulcerative colitis, which is one of the forms of inflammatory bowel disease. This VSL number 3 is another very successful group of probiotics which is being used very widely. And it's the first, and I use group because there's 8 different probiotic bacteria in there. It's the first that's been used and prescribed around the world for the treatment of the ulcerative colitis and pouchitis forms of inflammatory bowel disease. So up until this time, which is about 10 years ago, all probiotics were simply from the health food store, but this is one which is now being prescribed medically, certainly in Australia and in the United States. So it's really, what I'm trying to show you is that probiotics have come a long way from 1917 to now, where you can actually have probiotics which are prescribed medically and which have got strong mechanistic information behind them as to why they should be effective. I will, before I move away from this topic, warn you that probiotics may not always be probiotics, and I've said this before, in that because a probiotic is useful in a certain condition, it may not be useful in another condition. And this is a condition in our laboratory where we measured the LGG, which is a very common probiotic. You'll see that in health food stores everywhere. And we tested this in a model of NSAID enteropathy induced by indomethacin. And basically what this is showing us in every case is that the LGG, and in this case a large value is bad, the LGG was actually basically exacerbating the damage caused by NSAID enteropathy. So this is showing that in certain circumstances a probiotic can actually induce an infection because the patient, or in this case the animals, were maybe immunocompromised. So we have to be very careful about a certain situation of giving a probiotic. There may be cases where it can make things worse. And I think that's a very important take-home message for animal studies, and it certainly is for human studies. So it's certainly important to match or associate the probiotic with the disease. If you understand the pathogenesis of the disease, it's much easier to select the best candidate probiotic, because then you can target the probiotic to the condition. And that's exactly where we're heading in, and I'll give you a couple of examples. So basically our strategy is we do some in vitro work, and we then take this through to animal model studies, and I'll focus on that today for this audience, even though most people have got a background in the veterinary arena. This is one example where we took a condition, and in this case it was a condition known as mucositis, which is caused by children who, or adults for that matter, who are being administered methotrexate, a very common chemotherapy drug. So this is given very widely. It's also being used for arthritis, and it's given very widely across a range of animal species for cancer treatment. In terms of its mechanism, it actually inhibits folate development through inhibiting DNA synthesis, and it causes a condition known as intestinal mucositis, which is basically an inflammation of the intestinal lining. So because this methotrexate is inhibiting folate bioavailability, we rationalized if we could find a probiotic bacteria that produced folic acid, it might be able to protect the intestine from chemotherapy. All right, so our logic was that if we could find such a bacterium, it could basically deliver folic acid to the lining of the mucosa and hence protect against chemotherapy damage. And this is a young boy who's suffering from mucositis. Clearly he's got alopecia as well from our hospital. So we did a search and we found out that there is in fact a range of probiotics which will produce folic acid, and they tend to be known as Streptococcus Thermophilus. So these are basically a benign streptococcus. It doesn't cause sore throat or anything along those lines. It's a benign bacterium, and it's one of the ones that's in VSL number 3 that I mentioned before. I'll just call it TH4 because that is the substrain. And I put this up on purpose because this is a probiotic which can also be used in pregnant women to try and prevent neural tube defect. So it's got a range of different applications, but is it of any value in protecting the intestine? Well, what we did is we developed a test, and this is something I'd really like to express because this is a test that we'd like to develop in a range of different animal species. And I'll take you through how the test works, and I'd like you to think about the ways this test might be useful in the animal species that you work with. It's called the Sucrose breath test, and I'm digressing a little bit because this is a test that we used and we are using currently to try and monitor the effects of probiotics. So to go back a slide, we've got this probiotic which I'll call TH4. We want to see if it can protect the intestine. This is a test that we've developed to try and do that by an ethical, non-invasive means. So this boy is drinking a solution of sucrose. It's just analytical grade sucrose. It's not radioactively labeled in any way. But the sucrose has a natural non-radioactive label called carbon-13. So this is not carbon-14. I assure you, research ethics committees do not like you giving carbon-14 to children. I can speak from experience. They are very happy to give carbon-13 sucrose to children. So that sucrose passes through the stomach and it then passes to the small intestine down here, keeping in mind this is just sucrose that the boy drank. These are the villi that are lining the small intestine, the absorptive villi, and they have an enzyme known as sucrase, which is in the brush border of the intestine. The sucrase enzyme breaks down the disaccharide sucrose to glucose and fructose, the two monosaccharides, and as you can see they're still labeled with carbon-13. This is then metabolized by the liver to carbon dioxide, which is again labeled with carbon-13. So the carbon dioxide passes to the lungs, where of course accumulates in the lungs and then passes out as carbon dioxide in the breath. So once that's in the breath, we can collect that very easily. This is a little boy who's collecting breath into what's known as a vacutainer in a tube. We are also doing this in humid cribs with babies at the hospital, and we are doing it with pigs. We are doing this with rats. We're just in the process of developing this in the horse, and what we would like to do is to take this test on to cats and dogs and whatever species that we can perhaps talk about a little bit later in the day that you might be interested in. So how is that going to help? We've collected carbon dioxide, and these are basically rats that have been treated with methotrexate, going back to my TH4 story before. So these are rats that we've basically just administered chemotherapy. We're collecting their breath, and we've conducted the sucrose breath test, and this is the kind of profile that you get in the normal situation. So this is normal sucrase activity. These are animals that have been treated with methotrexate. They've clearly got a significantly reduced sucrase activity. So this is a test that the animal ethics committees are very happy with because we don't have to kill the animals to monitor their bowel function. And that's what we're doing routinely now in humans. And I would really like this test to be taken onto other species. It's very simple, and it's an indicator of total sucrase activity in the intestine. So if I just go back to the situation with TH4, the probiotic that I mentioned before, these are normal rats here, so this is the normal sucrose breath test value here. it's really quite high. When we treat with methotrexate, the chemotherapy drug, we basically get a 50% reduction in sucrase activity. Methotrexate hits the small intestine very hard, diminishes sucrase activity significantly. When we administered the TH4 probiotic, I think you can appreciate that there was an increase, although not completely back to normal, but it was a significant increase and an improvement in bowel function. And we were able to reinforce this with other indicators. This is the paper. It's some time ago now that we did this work. And again, it shows that biochemically and histologically it all reinforces this test. So it really negates the need to kill the animals. When we gave a lower dose, of course, we've started to titrate out the effect. Comes back to my point before about the amount of probiotic is very important. And of course, the study we'd like to do is to give even higher doses of that probiotic to see whether we could completely protect the intestine from damage. So I think that's perhaps a good example of a targeted development of a probiotic for a certain condition. And that's being taken forward now into human studies. To give a second example, we have a group of collaborators in the University of Queensland to our north, and they are working on developing different bacterial species. And they were able to develop one called Lactobacillus fermentum, I'll just call it BR11, which was basically a new species found about 8 years ago. And they were able to report that this organism produced very high levels of what's known as thiols, which are potential antioxidants. And this was through, and I won't go through the background of this, what's known as the cysteine transport system. So basically they produce large amounts of these thiols, they secrete them out into the lumen, and they're potential antioxidants. So we rationalized, if we could have an inflammatory situation, that this might be a good organism, and we didn't know it was a probiotic at the time. It was just a bacteria. We thought it might be very useful for mopping up oxidant species. So we tested this in an animal model, and again, this was a rat model of colitis. It's called the dextrans sulfate sodium model. This is the normal colon, and of course, this is the colon over here, which is damaged by dextrans sulfate sodium, and it gives the features of ulcerative colitis, or inflammatory bowel disease, or Johne's disease for that matter. When we administered the BR11, which is over on the right panel here, over time, the dextrans sulfate sodium model increases disease activity. Hence, you can see the black bar increasing with time as the colitis is getting more and more severe. We administered the probiotic, which is the BR11 on the far right panel here, and I think you can appreciate that in each instance there's a significant decrease in the disease activity in the colon, and it really is quite marked. So what was going like this in the normal colitis situation was only going like this in the BR11 treated group of animals. So this is what we're calling an antioxidant or an anti-inflammatory probiotic. And I think this has got a lot of potential in animal situations, in species characterized by colonic inflammation. And this is just some other pieces of data here. This is showing crypt depth, which is increased in inflammatory bowel disease. And again, on the right-hand side here, we can see it's basically back to normal. So this is just another indicator that this bacterium was having a probiotic effect. And this was some information that we've subsequently got on about the mechanism. I won't go into that now. But basically what that was showing us is that we have been strategically able to develop an anti-inflammatory probiotic. So this is basically our bread and butter now, is trying to develop strategic probiotics which can be used medically and out in the field for animal studies. More recently, we're working in the area of probiotic-derived factors. I touched on that initially, that you may not require the living organism to have the same effect as a living probiotic. And this was found about 10 years ago. There's a reduced risk of bacteremia. I found out that if you go to a treating oncologist in a hospital, they are not very keen on you giving immunocompromised cancer sufferers bacteria, because that's obviously a source of infection. But they are more happy if you give them non-infective products released by those bacteria. And this has been a strategy that we're working on more recently, and it's one that we're doing right now, and these are papers that you might want to look at. And this was one that's just been released a couple of months ago from our group, And it's really showing that this E. coli Nissl 1917, that some of the properties of that can now be endowed by the supernatants. You can spin out the bacteria and just use the supernatants to get the same effect. And I think this is perhaps the way of the future for a lot of probiotic research. I'll just move on to prebiotics now, and I won't talk about this quite as much, but prebiotics have been used very widely. In simple terms, they promote colonization of the bowel by probiotic species. Prebiotics are not metabolized in the small intestine. They pass straight the way through to the large bowel, and they cause a selective colonization of the large bowel and alter the microbiome. The prebiotics tend to have very long names like fructo-oligosaccharide and galacto-oligosaccharide. We tend to call them FOS and GOS for simplicity, and resistant starch is another good example. One of the benefits of prebiotics is that they will cause global changes and shifts in the microbiome composition, whereas a probiotic will only produce a local and very specific shift. And of course, this can work to your effect, but of course it can be quite dangerous if you produce a global shift which is in the wrong direction. Now again, prebiotics have been around for quite a long time. I know it's used quite commonly in dog food, etc., and pet foods, but again, the question is always asked, is it the appropriate prebiotic, and is it always going to be beneficial? And I'd just like to show you some examples that some prebiotics are not particularly beneficial. And this is FOS, very common prebiotics used very widely, and we've tested this in an animal model of inflammatory bowel disease. And in this particular case, where we're using the DSS colitis model that I mentioned before, and again we've got FOS over here, the panel over here, and what you can see, because in this particular case this is disease severity and big value is bad, we can see that if anything the FOS, it certainly wasn't doing anything, but if anything it might have been making matters a little bit worse in that situation. So we looked a little bit further at that, and we looked at an indicator of bowel inflammation. This is myeloperoxidase activity, which is basically an indicator of neutrophil infiltration. And we found that, lo and behold, again, FOS was increasing the amount of inflammation in that particular situation. And if you look at the literature more recently on FOS in human inflammatory bowel disease, and I reviewed this just last year, you'll find out that there's quite a lot of information that in humans taking FOS prebiotics with inflammatory bowel disease, their disease gets worse. So this is again saying that one of my take-home messages is don't assume that all prebiotics are good for all conditions. Certainly in certain situations they're fine. And this is another example here, FOS increasing the weight of the cecum. And in fact it tends to increase the amounts of organic acids. So it's basically adding an irritant in the inflammatory bowel situation. So this is more or less summarizing what I just said. In this particular case, the prebiotic FOS, which is anecdotally one of the major prebiotics, failed to protect the bowel from DSS colitis. And in fact, this maltodextrin was more effective. And there were some indications that that prebiotic could actually exacerbate the injury. And again, I've just mentioned before, there's a couple of review articles on this, and I would urge you to have a look at this particular commentary that I wrote in the Journal of Nutrition a couple of years ago, because it's basically talking about the association of certain prebiotics with certain inflammatory bowel conditions, and where some might be contraindicated. So any of you using prebiotics in your animal species, you might want to look seriously about whether it's the appropriate one and whether in fact it's going to do nothing, which could be very economically unproductive, or else it might make the situation worse. I'm just finishing off now by talking about symbiotics. Again, I see this perhaps as a way of the future as well, and it's basically a symbiotic, no big surprise, is the combination of a probiotic with a prebiotic. And again, I put the word S in brackets here because sometimes combinations of probiotics and prebiotics are more promising than the single species. But again, I'd really highlight that it's critical to optimize that combination, and animal model studies are really very important. I put this up on purpose. This is a paper we published in Nutrition and Cancer about 6 years ago, but in terms of probiotic combinations, there are very few papers out in the literature looking at those combinations. In fact, There are only 2 in the context of chemotherapy-induced mucositis in the entire literature in the world, and one of them is from our group. So again, this is an area that we're really starting to move into, because that's a whole niche area. But it really is very important to try and get the right combination. And to do this is really not just a case of grabbing a probiotic and a prebiotic and throwing it together like you're baking a cake and hoping that it works out. It's trying to work out the mechanisms of each of those species, putting them together strategically, and then testing them in animal model systems. And again, what I would like to say is that the inclusion of probiotic factors secreted from probiotic factors could come up with some very novel symbiotics. And to the best of my knowledge, there are virtually no groups in the world who are doing this at the moment. So again, this is an area that we see as really a very lucrative area to move into commercially as well. So I think this is virtually my last slide. I'd just like to finish up by saying, in terms of probiotic and prebiotic use for animals, and again, this audience is very interested in this, I understand, is that they are used in a very widespread fashion at the moment, but I would say they're not being used very strategically. They can be used as antibiotic replacements. There's a huge amount of work going on in Europe about looking at substitutes for antibiotics, and they're looking very long and hard at probiotics, but I think they're looking perhaps a bit too aggressively in a slightly panicked way. They're not looking at the mechanisms of which is going to be the most appropriate. There's also evidence in marine nutrition. We have got a big group working off South Australia, working in abalone farming and also in tuna and kingtail yellowfish. And we're also looking at a range of smaller fish in this arena to look at probiotics in that setting. And that this is really showing a lot of promise. And you might want to look at some of our recent work on this. We're working very aggressively in this area. So certainly we're getting an improved understanding of the microbiota composition, which is making life a lot easier to develop these probiotics and prebiotics in a targeted way. And I'd just like to finish up by saying in the last couple of slides, probiotics have got a lot of therapeutic potential. All those questions need to be asked: which one, when do I give it, how often do I give it, what are the long-term effects, and which do I really need the living organism? And predictive screening systems are really very important. And again, this is my last slide. I'll put this down here because animal model systems are really very critical to develop new prebiotics and to develop these new symbiotics to address and answer some of these questions. I'll just finish by acknowledging the Women's and Children's Hospital, and this is Professor Ross Butler, who's one of the inventors on that sucrose breath test, 2 of the postdocs who did much of this work, and the group at the Queensland University. And I'll just finish with a view out of my window of Adelaide on a nice sunny day. Thank you very much for your attention.